Is it okay, ma'am?
Sir, your slides are changing. Okay, sir.
Okay, ma'am. Good. Am I audible?
Yes, sir. You are audible.
Thank you, ma'am. Thank you.
Good afternoon. Lakshmi madam, good afternoon. Madam, please, you unmute your mic.
Yeah. Good afternoon.
Good afternoon. Kavita, shall we start? Okay. Sir, our principal madam has joined us, sir, Dr. N. Lakshmi. She has joined, sir.
Welcome, sir.
Vanakkam, madam. Vanakkam.
Welcome, sir.
Thank you, madam. Thank you so much.
Thank you for the support you are extending to us.
Oh, it's my pleasure. It's my pleasure, ma'am. Absolutely.
Thank you, sir. Thank you.
You're welcome.
Good afternoon to everyone. We are privileged to host this program and we welcome you with open heart and open mind for the 1 week national level faculty development program online.
Prayer is the key that unlocks the door to divine healing and transformation.
கருவாகி உருவாகி எனையாண்டு காத்தருளும் இறைவா நன்றி. எங்கும் நிறைந்தோனே எல்லை இல்லாதோனே சுற்றம் அனைத்தும் காப்பவனே செய்தொழிலில் ஏற்றம் தருபவனே எடுத்த செயலில் வெற்றி கொடு என் ஆற்றல் பெருகிட அருளை கொடு.
Thank you, girls, for the beautiful song.
All the powerful speeches ever made point to a better future. Now I welcome our esteemed Principal Madam, Dr. N. Lakshmi Ma'am, to give a keynote address for the program.
Dear participants, good evening. At the outset, I would like to thank our Secretary, Srimati Sumati Krishna Prasad, Director, Dr. J. Manjula, the Department of Physics, HOD, Dr. S. Aram, and FDP Coordinator for giving me this opportunity. 1 week national level FDP and a DBT star status scheme on development of material characterization techniques and their future prospects is organized by the Department of Physics from 18/12/23 today to 22/12/23 in online mode. I congratulate Dr. B. Kavita, FDP Coordinator, Dr. S. Aram, HOD, for ensuring a good number of participants from varied states from all the directions. The overwhelming response shown in registration, demanding closure of registration itself, confirms the significance of the topic and how good the resource persons arranged are. With the blessings of the God Almighty, I am sure the department is going to add another feather to the cap of GVG VC at the national level. I wish and pray to God that the next program organized by the department should be at the international level. I am not a person with physics specialization, but I could say most of the aspects in spiritual environment is always based on physics. Planetary position, astrology are all basically physics. Materials characterization techniques may typically be done in situ or ex situ using a number of possible methods such as optical microscopy, etc. As a commerce person, I can say that every industry incorporates various quality products, controlling their metallurgical structure and surface conditions. Manufacturing of high-grade products, short supply of raw materials, rising cost over the years has increased the requirements for technology for the effective to come and their manufacturing processes. So I am sure that this FDP, with the support of the great resource persons like our Dr. K. Gunasekaran, University of Madras, Dr. R. Raghunathan, Center for Bioscience and Nanoscience Research, Coimbatore, Dr. Pradeep Sharwade, University of Mumbai, Dr. Anantarajan Sengi, IIT Kanpur, Dr. Venkatakrishnan, IIT Mandi, will illuminate the participants to bring out more and more patentable, innovative ideas. I wish the Department of Physics all success in conducting the week-long FDP. I wish and pray to God to shower His blessings to the department to bring many intellectual properties to add glory for our institution. Thank you for the opportunity.
Thank you, madam.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Challenges are an opportunity to test you and rise to the next level. Now I welcome our respected Dr. Yes, Aram ma'am, Head of the Department of Physics, to present a welcome address for the program.
Good evening to one and all present here. It is with great pleasure and honor I stand before you today to welcome you to this distinguished faculty development program in the Department of Physics. This gathering marks a significant moment in our academic journey as we come together to enhance our knowledge, skills, and expertise in the fascinating field of physics. We are fortunate to have a diverse and accomplished group of educators and researchers in our midst, representing the rich tapestry of our academic community. The faculty development program serves as a platform for us to come in our professional growth, fostering an environment of continuous learning and collaboration. As educators and researchers in this dynamic field, we are entrusted with the responsibility of nurturing the next generation of scientists, thinkers, and innovators. This program provides us with the opportunity to refine our teaching methodologies, explore cutting-edge research, and engage in fruitful discussions that will undoubtedly enrich our academic endeavors. Throughout the course of this program, we will have the privilege of learning from distinguished experts and sharing insights with our esteemed colleagues. The exchange of ideas and the collecting pursuit of knowledge are at the heart of what makes our academic community vibrant and progressive. I encourage each one of you to actively participate, ask questions, and engage in the various sessions planned for the program. Let us seize this opportunity to broaden our horizons, deepen our understanding, and build lasting connections with our colleagues. It is with great pleasure and anticipation that I extend a warm welcome to our distinguished guest and resource person for today's program. We are honored to have Dr. K. Gunashekaran among us, whose expertise and insights promise to enrich our understanding and inspire us in the field of X-ray crystallography and biophysics. Dr. K. Gunashekaran brings with them a wealth of experience and knowledge that has significantly contributed to the advancement of their field. Their education to research, teaching, and innovation has not only shaped the minds of countless individuals, but has also left an indelible mark on the broader landscape of physics. It is with great pleasure and honor that I extend a bouquet of welcome to our Gunashekaran sir. Please welcome, sir. Now it is with great pleasure and honor that I extend a red carpet welcome to the most respected and beloved Secretary Madam, Srimati Sumati Krishna Prasad. Our Secretary Madam has demonstrated exceptional dedication, leadership, and a profound commitment to the betterment of our institution. Once again, I welcome our Madam Secretary in her absentia. It is a privilege and a moment of great pride to extend my red carpet welcome to our esteemed Madam Director, Dr. J. Manjula, who has 45 years of academic excellence. With a wealth of experience and a visionary outlook, our Madam brings a wealth of knowledge and leadership to guide our institution to new heights. Welcome, ma'am. Now I welcome our beloved Principal Dr. N. Lakshmi, who has 35 years of service in her academic excellence. Welcome, ma'am. Now next I would like to welcome our faculty friends and all the participants. As we embark on this journey of professional development, may we embrace the spirit of curiosity, collaboration, and commitment to excellence. I wish all a rewarding and enlightening experience throughout the program. Welcome.
Thank you, ma'am, for the admirable words.
Now the session will be continued by our respected resource person, Dr. K. Gunashekaran sir.
Sir, before you start, sir, actually, we have received more than 600 participants as a registration, sir. So we are live streaming our FDP, sir.
So they don't need to register directly. I mean, they don't need to join here.
Yes, sir. Yes, sir. Yes, yes sir. Live stream is going on, sir.
Okay, okay, got it.
Thank you, sir. Thank you, sir.
All right, thank you so much. So FDP, Faculty Development Program. Normally, we used to undergo refresher courses and then orientation courses in those days, like 3 weeks and 4 weeks, 28 days for orientation and 21 days for the refresher courses. It was too big, and then financially as also it is so cumbersome. To avoid, and then one thing would like to say, எல்லாத்துலயுமே ஒரு positive, everywhere there will be positive, right? During Corona, we suffered a lot, but we started learning through online. That is one thing happened. So we nowadays even refresher courses are conducted online. All right. Since it is a huge number, it seems that it is online streaming directly. Okay. Anyway, fine. The only thing is, the only bad thing is I could not see you people. You could not see physically, because personal touch is so important. When there's a big hall of many people, we will be happy to talk to them. Anyway, I'm now talking to the computer, but indirectly to you. Okay, it's a good opportunity. So personally, I thank the convener madam and the college authorities who permitted me and then who appointed me as a resource person. And afternoon hearing is always difficult after good food. Normally, when it is not after food, it is 3 o'clock. So it's good. So they said 3 to 4. No, X-ray crystallography is not a subject to discuss within an hour. at least we need 3 days to 3 hours, so 9 hours. If it is 9 hours, probably we may have some idea. But anyway, so let's see what can we do within this an hour. Basically, I am a chemist, first of all. I'm a chemist. I'm working in the department of crystallography and biophysics. So this field is highly interdisciplinary. Okay, fine. So without X-ray diffraction, no science is complete. You must be knowing by this time. Whether you are a physics, material science, or life science, biochemistry, molecular biology, whatever, or chemistry, organic chemistry, synthetic chemistry, whatsoever, without crystallography, the science is incomplete. It's a small bit. Crystallography is a small bit, but becomes an essential bit to solve the basic question. What is the question? Structure. Without structure, any understanding is incomplete. All right. So I'll try to share my screen here. Entire screen. Okay. Hope you can see my slides now. Yes. I'm sure you can see. I'm sure you can see the happy face here.
Yes, sir.
Yeah. Okay. So this is the last slide of this talk. So we will have the complete structure. Obviously, we'll be happy. Things are like, even if you're a molecular biologist or a biochemist, you find a small peptide which has anti-cancer activity or anti-tuberculosis activity, or a small protein which could inhibit the amylase protein or protease protein, or it stops some kinase, or if you take a structure of an enzyme which does work, right, to convert the substrate into the product, means sometimes a substrate can be cleaved into two portions, or two portions can be joined. That is another enzyme. Ligase is an enzyme which connects two DNA pieces. Protease is an enzyme which cuts a protein into two pieces. So there are many enzymes and many receptor molecules. You may be knowing by this time, insulin is a small hormone which goes and sits on the cell surface, so that there is another gate opens, so that the glucose can enter into the cell for the energy. When insulin is not working, the gate is not open, so the glucose cannot enter into the cell for the energy metabolism or energy usage. So you may have a lot of glucose at the periphery, but the cells cannot take the glucose inside unless and until the door is open. Who opens the door? Insulin. So insulin is the key, let's say. On the cell surface, there is a protein called insulin receptor. So this goes and sits there so that the other gate opens, so glucose enters. You know this. And hemoglobin is a protein. It's not an enzyme, it's a protein which takes oxygen, right? And then why it is taking oxygen? Because it has the affinity towards oxygen. So it takes up the oxygen. Who supplies the oxygen? From the lung, whatever it is. So hemoglobin takes up the oxygen and then goes every single corner of our body. When it reaches that point, its affinity towards oxygen is minimum. So oxygen is get released. But now the hemoglobin becomes more loving towards, or it has more affinity to carbon dioxide in the form of carbonic acid. So carbonic acid binds with the hemoglobin now. Hemoglobin, which has the strong oxygen affinity at the lung, now it has the least affinity towards the oxygen, whereas it has a high oxygen affinity towards the carbonic acid. And then when it is coming back to the blood, heart, and then here, what happens now? It becomes more oxygen affinity. So carbonic acid is released, so oxygen is taken. Correct. So this carbonic acid is divided into two portions, into carbon dioxide and water. Water will be retained, carbon dioxide will be sent out by another enzyme called carbonic anhydrase. Hemoglobin is the one transport oxygen and back transport the carbonic acid. Carbonic anhydrase is an enzyme which cuts the carbonic acid into carbon dioxide and water. You know what? The same carbonic acid in the cells has different function. You know what is that function? It attaches the carbon dioxide and water into carbonic acid. See how beautiful it is? The carbonic acid of the cells connects carbon dioxide and water. The same carbonic anhydrase, different isoforms, slight isoforms. and in the lung, it breaks the carbonic acid into carbon dioxide and water. Hemoglobin takes oxygen here, whereas in the cells, it takes carbon dioxide. Same molecule. See, different molecule, different function. Here, same molecule depends on the environment, it changes its function. Okay, fine. Now I'll go to the first slide. Very simple slide, which you all like, and then you would have seen sometime. Okay, fine. All right, see that? See, there are three things are shown here. I'll just go quickly. So this is called spanner, and then you know what is it? What is the function? You know what is the function? It tightens the nut or loosen. Correct? Fine. When it will work, say for example, this is a big structure, but the whole structure is not important for the function. Actually, function is happening only in this portion. So the rest of the portion are helping or handling. Correct? So this is the active portion or catalytic site or active site. These are the structural portions. Okay, fine. Good. In the protein also, very big molecule, but only a small portion is doing the job, doing the work actually, catalyzes the reaction actually. That is called as active site. The whole thing is a one single protein. The whole protein may be big, but the active site is small, where actually function happens. Okay, fine. When it will work only when the shape and size fits well. That means two parameters, shape and size. If both shape and size are compatible to the active site, it will work. Okay, someone has saw this and then they understood how it is working. They developed this second one. You know, the beauty of the second one, it doesn't worry about the shape. It worries about the size. If the size fits, whatever the shape, this will work. The only thing is size should fit within the packet. Then it will do the same job. Okay, fine. Someone has developed this one. In this case, even size is not important. You can adjust this in such a way it can fit smaller one or bigger one, or little bigger one, or maybe smaller one or bigger one. So size as well as shape doesn't matter. You know what is this? It's called evolution. Someone saw this, they understood how it is working, they changed this. They engineered this one. What engineering is this? Okay, I'll tell you. And then once again, they engineered this one. All right. Now, for example, these three. Now you can see these three also here. All these things can be used to make a whole, but this is different function, this is different function, this is different function. There are similarities, there are dissimilarities. Why? There are small structural changes. And actually, so you can see these two. For example, if I can drink tea in this, no problem. The only thing is, when it is hot, I may hurt. So what I'm doing, I have added some extra stuff here so that I can handle easily. What is it called? It is called structure-activity relationship. This structure is important for this function. If the structure is not existing, the function is lost. Actually, recently one of our professor, actually she is a Nobel laureate, she was in Chennai last 2 years back. She explained in a very beautiful way. You take the gem clip. Gem clip is for holding the paper. When you open the gem clip, what happens? The structure changes. Now it becomes some S shape. Now this can be used to hang something on the thread. So when structure changes, function changes. This is called structure-function relationship. Using this relationship for these things, convert this into this and this into this, or this into this. It is called as structural engineering. Okay, fine. Okay, this is also another example, very small example. Don't worry, it is a very lighter portion. So in this case, these two are same type of, two molecules having same carbon numbers and the hydrogen numbers and oxygen. Element-wise same, but the structures are different, right? This CH3, CH2OH, this is CH3O, CH3. What is it? Very beautiful. So what I'm going to tell you, very simple. If Gunasekaran drinks this, Gunasekaran will dance. If Gunasekaran drinks this, then people will dance around the dead body of Gunasekaran. The only difference is this. Why these happen? Because the structure are different, right? When the structure is different, the function is different. Why? Because this molecule may fit with some protein, which is responsible for sending some good signals, happy signals to brain, so I'm dancing, maybe. And this is another key. This is a small key, another different key. It fits with a different protein target, different lock. So here it performs some function. Maybe the protein is essential for the life. Since the protein is locked, I may die. So there's the difference. What is it? Why this happening? Structure is different, so function is different. Okay, I don't want to go in detail, but just I will say one thing. Proteins. We are protein crystallographers. We do protein structure determination in our lab. Proteins are polypeptides. One amino acid, another amino acid. This is, for example, amino group, this carboxyl group. Amine group, carboxyl group joined together makes a peptide bond or amide bond. And another one, and another one, another one. It's a big chain. If it's a chain, it's just a polypeptide. When the chain folds into a three-dimensional structure, then we call it as a protein. Right? All are made up of amino acids. There are only 20 different amino acids. These 20 different amino acids making polypeptides, they fold in different three-dimensional structure. Why? Different function. They are supposed to do different function. This is hemoglobin for oxygen transportation. This is the helicase which is useful for the DNA unwinding. This is another protein. This is another protein. This is another protein. Different functions. All are made up of, once again, all are polypeptides. Only the way they folded a chain, it is folded. For example, so this is a chain, it is folded into a different shapes. Why different shapes? Because they are supposed to do different functions. All right. So, okay, I don't want to go in detail about this. I'll come back. All right, sir. Now, very simple. Now we all agree structure determination is essential. Right? Take a stool. It's just we can sit. Someone added a back portion so that we can lean back. And then someone added 2 arms so that we can rest our arms. And then there is a foot rest. And then you press a button, it will go back. You can be a recliner. What is this all? These are all modifying the structure to attain different functions. When you can modify the structure, if you know the structure, if you know the function, then that will be useful for a structural engineering. Make as, for example, a synthetic molecule, and then we know this contains this molecule. For example, by adding one methyl group at this position, it may become aromatically good smell. If you add some other group somewhere, it may give a different bad smell. And then some will be drug, some will be poison, some will be good for, different things. All are what? There are only elements, the way they are attached, the structures are different, so functions are different. So structure determination becomes essential. We all agree with that. Am I right? Okay, fine. Now I'm going to ask you. Ma'am already said physics is an astrophysics and everywhere. Basically, without physics, we are doing. We say we are walking. Walking, we say walking. Actually, in physics, it's called controlled falling. We are falling. I'm falling, but I'm changing the center of mass by putting one leg here so that I'm not falling. Again falling, I'm changing the another foot so I'm not falling. So continuously I'm trying to fall, I'm trying to prevent it. It is called walking, right? Okay, I'm going to ask you one question. Am I opaque or transparent? Am I opaque or transparent? Okay, fine. I am opaque. Then you are, that means what is opaque means? Opaque means light is not passing through, right? Okay. Why am I opaque? Why am I opaque? Okay, once again, I am opaque, but to some rays, I am transparent. You know what it is? Of course, X-rays. When X-rays falls on me, it penetrates through me and then comes out. So with respect to X-rays, I am transparent. Forget about my bones. Forget about my bones. Basically, I'm opaque with visible radiation. I am transparent with X-rays. What is it? When some light falls on some material, right? If nothing is coming out, it's called opaque. Why nothing is coming out? Because all the energy is absorbed by the system. Right? The energy which I am supplying or which I am making to fall on the material, if the energy is of the interested range of this material, that will absorb all the energy. So nothing will come out. Then we call it as opaque. When I am supplying energy, whatsoever energy, if that energy level, that energy is not interested range of this material that will allow the rays to pass through it. That's all. Right? Suppose if I am hungry for 5 days, damn hungry. If I am in a forest, I am deadly hungry. Suppose if someone appears in front of me, and then if I say, okay, do you want 2 chapati or 2 lakhs rupees? Which I will select? I'll select 2 chapati. Why? That is the energy I am interested in. That. Correct. So when 2 lakhs rupees and 2 idlis are passing through me at that time, 2 idlis will be absorbed. 2 lakh rupees will be passing through me because I'm not interested in that ray. That's what it is. Fine. So what happens now? I will come back to somewhere. You just watch this. All right. See, there you can, how can I make it bigger? I don't know. Bigger. But anyway, I hope you can see this screen now. So now what happens is, so this is the molecule. We have a molecule here. See that? See that? There is a molecule. Okay. So this is the molecule. Okay. I'll show you another thing now. Okay. This is the molecule. You know what is this? This is called chemical sketch. Right? Chemical sketch. This is a 2-dimensional sketch plot. I have drawn, there is an indole, I guess, indole, and then there is a sulfophenyl, and there is a carboxylic acid group and so on. What is this called? This is the chemical sketch. What is the 3-dimensional structure? It is not 3-dimensional structure anyway. Correct? Someone, they synthesize this compound, and hopefully, they don't know what they synthesize, they're expecting this compound to be formed. It has to be verified using IR, NMR, everything we can do. The 3-dimensional structure can be arrived only using X-ray crystallography. Sometimes NMR can give, but most of the time we have to rely on X-ray crystallography. And X-ray crystallography is the only tool to determine the 3-dimensional structure of any molecule, be it small, medium, macro, without any prior information. You don't need to tell me anything. For example, in this case, I'm going to tell you how to solve the structures briefly. In this case, structure is known. Someone has, but without knowing also you can solve. It's not a problem. With structure is known, you can solve the structure in half an hour. If it is anything, nothing is known. Probably even in the case of protein, if you don't know anything, probably you may need to use some special technique. For example, if it is a regular protein whose structure, corresponding structure from some other species available, we can use molecular replacement technique. If nothing is known about the protein, I got only crystal and then I got X-ray diffraction data, still you can solve the structure using multiple anomalous dispersion technique or multiple isomorphism replacement technique or multiple wavelength anomalous dispersion technique. But anyway, I don't want to go in detail. What I'm telling you is crystallography can give you structure without any prior information. But we should have a crystal. And then we should have a diffraction data. Only these 2 things. Now, for example, structure is essential. And once again, I'm sorry. So let me show you the unit cell box. See that there is a unit cell box. There is a unit cell and our molecule is here. How it is? Okay, see? And see? All right. See? Oh my God. So this is what it is. Okay, so many molecules, correct? So many molecules are arranged in the crystal, right? What is crystal? Crystal means clear. Crystal means pure. That means if I am crystallizing A, whole crystal contains the molecule only A. Correct? Whole A. Millions of A's arranged inside the crystal. Only thing is when I say arranged, means one A is like this. Another A like this, another A like this, like this, like this, like this, like this. So some kind of symmetry relations. Generally, if there are chemistries in this audience, I warn you that in chemistry, we are talking about the symmetry within the molecule. For example, water. Water is, there is a 2-fold rotation. Probably you know. We are talking about the symmetry within the molecule in chemistry. In crystallography, between the molecules. For example, that's what I'm saying. Suppose water is crystalline, let's say. One water, V shape, right? V shape. Another 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 V shape. So what is the symmetry relation between different water molecules? In crystallography, we are talking about the symmetry between the molecules. not within the molecule. Be careful about it. Very small thing. Okay, fine. Now, in crystallography says, if you crystallize anything, you must be knowing 7 crystal system, 14 Bravais lattices, and there are symmetry. For example, these two, what is the symmetry now? Hope you can see my hands, palms. What is the symmetry? There is a mirror between. Suppose if it is tilted like this, then it is called two. For example, this hand, if I am having a axis here, if you rotate twofold, that is 180 degree, right? So this one and this one. Now there is a symmetry is twofold rotation. This one and this one, there is a mirror. Correct? So you know twofold, threefold, fourfold, sixfold, and mirror. You know all these things. And then center of inversion. One is like this. Suppose if one is like this, upside down, then it is called inversion symmetry. You know all this. Along this, apart from this, there are 2 extra symmetries allowed in crystallography. Means you would have seen people are walking in the beach. 1 foot here, 1 foot here. 1 foot here, 1 foot here. And then probably we may say there is no symmetry relation between them. No, we have. Means you take the first foot, okay? You take the first foot and then get the reflection. It will be here. Now it is reflection. Instead of here, it is here. That means it's called reflection followed by translation. In the walking beach, 1 foot, 1 foot. What is the symmetry between? Mirror followed by a translation. It is called glide plane. That's why I hope you can see me. From here, it goes here and then move. From here, move, mirror, go, mirror, go, mirror, go. Right? Yeah, mirror, a reflection by a translation. From there, mirror, reflection, translation. Reflection, translation, reflection, translation, reflection, translation makes your beach walking. Right? You can see when somebody is walking on the beach, you can see 1 foot and then 1 foot, 1 foot, 1 foot. What is the symmetry between them, among them? It's called reflection followed by translation. It is called glide plane. It's called glide plane. If it is along A axis, A glide, B glide, C glide, they are different. Don't worry about it. Apart from rotation and then reflection, right? Center of inversion 3. In crystallography, reflection followed by translation is allowed, which is called as why? Because, for example, no translation symmetry allowed in chemistry within the molecule, because we are talking about within the molecule. But here we are talking about between the different between different molecules of same type. Got my point? That's why in crystal, one molecule will be here, one molecule is here. Then we say there is a reflection symmetry. If there is a molecule here and there is another molecule here, it is called as reflection followed by translation, which is called glide plane. Glide plane. Similarly, rotation 180 followed by translation. Again 180 followed by translation. Again 180 followed by translation. It is called 2-1 screw. Twofold rotation followed by translation. So it's called as screw axis. In threefold, if it happens, it's called threefold, right? 3-1. All are called as screw axis. All right. Am I audible?
Yes, sir. Audible, sir.
Okay.
Yes, sir.
Thank you. Thank you.
Audible.
Thank you so much. So that's why. So in this case, for example, there are so many one type of molecule multiple times. It formed the crystal, and then it is like this. See? So many molecules are arranged within a solid, which is called a crystal. When it is crystal, it contains only one type of molecule. Second thing is they form with some symmetry. A periodic arrangement is there. It is not. That's why to achieve the periodic arrangement, there must be some symmetry relation between the molecule. There are some symmetries. Okay, as I said, inversion symmetry, rotation symmetry, reflection symmetry, and 2 extra: screw axis and glide plane. By all this combination, there are 230 different possible arrangements. That's called as space groups. You crystallize hemoglobin, you crystallize benzaldehyde, you crystallize benzene trinitro 1-toluene oxide, whatever it is, or even titanium oxide or gadolinium titanium tetrachloride, whatever it is, that should follow any one of the 230 different possible arrangements. That is called as space groups. Okay, anything. All right. So maybe in another, I'll just, yeah. Okay, let's see now. This is another view. Same thing, another view. See? So this is what, when someone gave me what I had, crystal. I don't know what is inside. Then what I do diffraction. From diffraction, what I do crystallography. And then I will get what? One stuff with the crystal structure. I get this structure. So this is the structure of the molecule. Okay? This is the structure of this. Don't worry about it. This is the structure of the molecule. And then I'll understand how it is packing. Because I know what is the unit cell dimension, A, B, C, alpha, beta, gamma. Then I know, okay, oh, this may be like this. Or maybe more and more. Or, okay. Or, okay. Or, okay. See that? How, yeah. Right? So these are the units. You can see the unit cell here. This is one unit cell. So like this, what? Hundreds and hundreds and hundreds of unit cells are together forms one crystal, right? So what is the unit cell dimension here? Here maybe 10 angstrom, 20 angstrom, 30 angstrom. So 20 by 30 by 10 cube. I mean, a small three-dimensional unit cell, which repeated thousands and thousands of times to get the crystal. So from the crystal, we are going today take the crystal diffraction pattern. So that crystal diffraction, we are going to solve the three-dimensional structure of that one single molecule present inside the crystal. All right. I'll close this. Then, oh my God. Oh my God. Okay, fine. Now we come back to our story. Structure determination is essential. Okay, fine. Then let me see. As I told you, when X-rays were discovered, people were everybody tried to understand the X-ray in their own way, what it can be used for and so on. You know, X-ray is the one technique or concept which was brought into practice as soon as it was discovered, right? Immediately it was useful in the war, because military men, when they had the wrecks and so on, X-rays were used to discover there's a bone break or something. X-ray is the one of the best discovery which brought into practice just like that, very quickly. All right. So someone wants to know what will happen when crystal is exposed to X-rays. Now I told you there are only two concepts. One is opaque or transparent. So if the crystal, if it is opaque, right, probably what will happen? In the screen you will have the dark shade. Okay. If it is transparent, then probably what you will get? A faint lining, but it will be completely transparent, right? So opaque and transparent. Now what happened when they placed the crystal on the X-ray path? They took the film. You cannot see anything, right? Only after development you can see. After the development you can see like this, then it is opaque. After development, if you could see this, then we can conclude it is transparent. Crystal is transparent. But what happens is when crystals are exposed, they got the film, and then when they developed, you know what happened? They got like this, spots. There are bright spots, light spots. Now they understood it is neither opaque nor transparent. But what happens when X-rays are penetrating through the crystal, it is getting diverted. It is getting diverted. It is colliding something inside, so it is getting deflected, right? It takes bent and then go and hit the screen. And then there are something here, there are something here, there are something here, there are something. Then they understood crystals are doing diffraction. So X-rays are diffracted by crystals. Right? You know that the diffractant grating we have seen in the schools, right? When there is a small glass plate, we draw very tiny parallel lines, Correct? Very tiny parallel lines. And then when you send some laser beam, maybe even a laser pointer, you can see it is getting deflected. And then, two slit experiment also, you can see the diffractor phenomenon. All right. Now, this is the story. This is the initial story. Okay, crystals are doing diffraction. All right. Then, okay, let's take a photograph. If I am allowed to take a photograph in this hall, right? There is a marriage hall. Then let's say what happens. Oh my God, I'm sorry. Just give me a moment. I'll back. So these are all our studies about what we do in our lab. Yes. Before going further, probably this is my important to tell you. Crystallography is one way a white collar job. For example, an organic chemist, he is setting up one particular synthetic route, and then he has synthesized 60 compounds or 80 compounds. And then he has analyzed all 80 compounds for NMR, IR, UV, and even sometimes mass spec, and so many things. When they send for publication, if it is an high impact journal, most of the time what they ask, can you prove any one of your structures using X-ray crystallography? Why? X-ray crystallography is authentic. No manipulation can be made. And then in crystallography structure, it is 0.9 angstrom resolution. That is atomic resolution. We can see atom by atom, three-dimensional connection. Correct. So that's why, not only that, crystallography data is verified by its own multiple times. The structure is verified by multiple times. That's why a crystallography report alone can be published as a paper. Nowhere in no single other technique cannot be published as a paper. But crystallography result, only one structure you can publish as a one publication, right? Not only that, you are going to deposit the structure also in PDB if it's the protein. If it's a small molecule, you are going to publish in Cambridge Structural Database, whatever. So one single experiment investigation results can be published, can be reported. If that is the case, there is only X-ray crystallography. Okay, all right. So that's why. So what will happen when a chemist, he has done a number of beautiful work, unnecessarily they have to come to us, a crystallographer, to get one structure, at least one structure. If that structure is coming out good, probably that can be published in a good journal. Obviously, crystallographer also will get a very easy publication. It's a white collar job. Anyway, why it is authentic? That's the important. There's authentic and ultimate. All right. So this is what the structure contains, and then we say three-dimensional structure. I showed you already rotation, so you don't need to worry about all these things. So okay, fine. Now let's see. Let's take a photograph. See now, people are sitting rows and columns like this. Okay. In the photograph, what is photograph? Oh, this is what photograph is. Correct. So I am going to use the camera here. I'm going to throw the light from here. I'm going to record it back. See, light goes from here and then comes back, which I recorded. So camera means light source as well as film are the same, on same side. Right? Okay. When we develop, what will happen? We'll get this structure. Yeah. So this. So when I'm taking a photograph like this, I'm going to get this. A regular photograph, this will be exactly how the people are sitting. Fine. Now, I'm going to change with your permission. I'm going to place the camera at the bottom here. I mean, what is this? It's a marriage hall. These many people are sitting here in rows and columns. This is the stage. Right? This is the podium stage. This is the background wall, the backside wall. I'm going to throw the light from you, from here. I'm going to record it back. For example, In the regular photograph, what is it? From the same side we throw the light, from the same side we are recording. That is the rays coming back, scattered back or reflected back. It is recorded. Fine. Now in this case, I'm going to throw the light from here. I'm going to record back this way. Okay. Can we do this? Okay, let's see what happens. When I'm taking this photograph, I got recording and then I developed the film. When I have developed the film, you know what I'm seeing? I'm seeing this. See, we are getting picture with only certain equally spaced rows. Row number 1, row number 5, row number 10, 15, 20, you know, like this. Middle people are not seen. Okay, let me do one thing. Be careful what I did. Camera is here. I am throwing the light from here. I'm recording here. Okay, I got this picture. Okay, now what I'm going to do, let me move the camera from middle to here, somewhere, right? Let me move the camera to the other corner. From here, let me take the picture. Let's say what happens. Now, you know what? Only certain equally spaced recorded, which is different from the first picture. There I told you 1, 5, 10, 15, 20. Now here 1, 7, 14, 21, 28, you know, like that. So only those, every 7th row is recorded. Middle people are not seen in the photograph. All right. Let me do one thing. Let me move the camera somewhere else. Let me take once again. What happens? Now see, to my surprise, now I can see row 1, row 11, row 22, row 33, row 44, row 55. Isn't it beautiful? Okay, let's see. So when I'm moving somewhere, imagine this blue lines. These are diagonal. This row is seen, and this row is seen. This row is seen. This row, this row, this row. Middle people are not seen. Okay, let me move the camera somewhere else, or maybe let me climb on the one big chair or table. From there, let me take. Now what happens? Okay, let's see. See that? Now this row, this row, this row, this row is seen. Middle, it is not seen. Middle, it is not seen. What is happening? What is happening? What is happening, man? What is happening? Very simple. People are sitting exactly the same way. And then recording film is also exactly in the same place. What I'm changing? I'm changing the position of the camera. I'm using the same light. I'm not changing. So the light is same. Correct. Okay. What is changing? Angle is changing. What is? Angle is changing. Angle of inclination is changing. Angle means theta. Same light means same wavelength. That means lambda. Lambda is always same. What I am changing? Theta. When I am changing the theta, what is the consequence? In the photograph, only certain rows which are equally spaced are recorded. Right? When I'm changing another theta, now the distance between this is changing. You got my point? When lambda is fixed, when theta is changed, different rows of different inter-row distance is recorded. Other people are not seen. Correct? Probably by this time, you must be remembering the equation, which is a very old equation, right? See, light is same, that is lambda is same. Different position of camera, that means angle are different. Same lambda. Okay, what happens now? For a given lambda, each theta make different rows of different inter-row distances, produce diffracted waves. Those can go and hit the screen. Got it? So this is what it is called. Yes, you got it. N lambda equals 2d sine theta. You know what it means? For that lambda, for that theta, suppose d comes as 5, means 5 feet. 5 feet, let's say. So first row, 5 feet. That row, from there 5 feet. That row, from there 5 feet. That row, only recorded. In between is not recorded. You got my point? When I change the theta, for that lambda, for that theta, The D, if you calculate, the D comes 7 feet, let's say. So that what happens? First row, 7 feet. That row, 7 feet. That row, 7 feet. That row. Only recorded. Middle, nothing is seen. You got my point? That is what happening. Okay, fine. Now, what is called inter-row distance? That's what inter-row distance. Fine. If you take crystal, if you take a crystal, and then if you pass through if you take the crystal like this and pass X-rays, the X-rays are penetrating towards the crystal, which is going in through the crystal, but for that lambda, for that theta, only certain planes, here it is rows, just for imagination, in the crystal, it is certain planes which are separated by a particular D. For example, 5 angstrom. That means one plane, 5 angstrom, another plane, 5 angstrom, another plane, 5 angstrom, another plane. These are all imaginary planes anyway. These are all imaginary planes. These planes, which are separated by 5 angstroms, only will give you the diffracted ray comes out. That can be recorded. Correct? For the same lambda, if I change another theta, now D can be 21 angstrom, let's say. So, from that orientation, that plane, maybe a diagonal plane, no problem. That plane, 21 angstrom, another plane, 21 angstrom, another plane, 21 angstrom, another plane, all these planes together, please remember that. All these planes which are separated by 21 angstrom, 21 angstrom, 21 angstrom, 21 angstrom, in that direction gives one spot. Okay? In the X-ray diffraction, you will get only one spot. One spot. That one spot gives by set of number of planes, not one plane. Be careful, right? For example, I'll go on and tell you. So this is the regular X-ray diffraction photograph of proteins, but don't worry about it. Suppose only one dot, let's say one dot. So this dot, or this dot, or this dot, or maybe this dot. So this dot is what? This is what? X-ray film. So this dot is produced by one set of planes inside. One set of planes. Forget about this protein crystallography. There is a small misconception may come into picture, but don't worry. What will happen? In those days, there is no film for recording in the X-ray diffractometer. There is a pinhole camera. There is a pinhole camera. So only rays which are going to the pinhole will be recorded. Okay. What we'll do, we put a crystal here, we open the X-ray here, the X-ray passes through the crystal and the detector will move like this. When it is moving, only one point you will get the diffracted beams comes out, that will be taken into that and that will be measured. That will be spotted. Okay. But anyway, now let me take this example. Now, what are these? Each dot is from one set of parallel planes. One set of parallel planes. Okay. What is our purpose? To solve the structure. Structure of what? Molecule. Where is it? Inside the crystal. How is it? These molecules are following by symmetry. They followed the crystal. They formed the crystal. Before that, actually, take one molecule, another molecule, another molecule, another molecule. Symmetrically, they place followed by two-fold symmetry, and another two-fold symmetry, another molecule. Another two-fold symmetry, another molecule. Let's say there are 4 molecules together formed a unit cell. That unit cell is multiplied into 3 dimensions to form the crystal. Okay. What are we doing? Structure determination. Of what? Molecule. Where is this molecule? Present in the unit cell. Present in the unit cell. I'm going to tell you one more small terminology here. Within the unit cell, suppose there are 4 molecules, let's say. One molecule, one molecule, one molecule, one molecule. Correct? 4 molecules. This molecule, two-fold rotated, comes here. Two-fold rotated, goes here. Two-fold rotated comes here, right? So these four molecules are having two-fold symmetry among them, correct? What is the unique means one single molecule where is no symmetry inside. That is called as asymmetric unit. Asymmetric unit is the minimum unit of the unit cell where there is no symmetry. That asymmetric unit followed by symmetry, it forms a unit cell. If four molecules can be in a unit cell, or 2 molecules can be in a unit cell, 8 molecules can be in a unit cell, whatsoever, no problem. Why? They are following some symmetry to form the unit cell. That unit cell multiply to form the. You got my point? Fine. Now, what is our purpose? We have to solve the structure of the crystal, structure of the molecule. From what? Crystal. That's why we call the structure determined by crystallography is called crystal structure. Okay, fine. Now, how to find it? We have to find out the electron density. Electron density. Where is electron density more? I place an atom. If there is an electron density more, I'll place an atom. Then, if they are 1.3 angstrom, I'll connect. Correct? So, wherever electron density, I place some atoms, and then connect them to get the three-dimensional structure of the molecule. Okay. For that, what we do? We have to calculate the electron density. From what? X-ray diffraction pattern. What is the pattern? The pattern is this. What is this? We know. See, for example, a spot is produced by the secondary waves from a set of planes which are separated by a particular distance, which satisfies the Bragg's law for that lambda and for that theta. Got my point? So, bottom, please carefully watch here. Each spot contains information about the scatterers present in that set of planes, not one plane present in that set of planes. You got my point? So, each spot contains information about that set of planes. What information? Electron density information. So, I want to find the three-dimensional structure of the molecule. So, what should I do? I take the crystal, hit, take a photograph, rotate, hit, take a photograph, rotate, hit, take a photograph, rotate, hit, take a photograph. Like this, rotate. Like this, rotate. Like this, rotate. Like this, like this, like this, like this, like this, like this, like this. So all possible way, I rotate, take one photograph. Rotate, take one photograph. Rotate. What happens? I'm using the same lambda. I'm continuously changing theta, another theta, another theta, another theta. For each experiment, for each spot, for each one collision, one set of planes information is recorded as one spot. Correct? So, if I process all together, what I will know? I'll find out the electron density within the unit cell. Within the unit cell. Correct? Electron density within the unit cell. How a unit cell is formed? By multiplying the molecule by symmetry. Now I am going to divide by the symmetry. I'll get the one single molecule structure or electron density about one single molecule. I'll stop here and then I just take one back. Now I have to tell you one important. Why it is so? For that lambda or that theta, only why one set of planes are recorded? Very simple. Just it is all not new to you. You would have studied already, but just one. So let's say this is one plane one. Like that marriage hall example, just take one row. This is another row. This is another row. Let's say one row, another row, another row, another row, another row. Let's say for that lambda, for that theta, right? Suppose 5 feet is the D value. Let's say that means one row, then not this row, not this row, not this row, and this row. That means first row and fifth row. First row, fifth row. In between, forget about first row, fifth row. Right? So I'm throwing light on all of you. There is no, I'm not showing any partiality. You people also, all these marriage, all people also doing scattering, reflection, anything and everything happening. Same. When bent beam, the fall and then take a deflected beam, which is going behind towards the backside, no, there is small difference. You know what happened? For that lambda, for that theta, suppose D is 5 feet, what happens? first row and fifth row. Let's say these two waves are traveling back like this. I hope you can see now. 1, 2, 3. What is this? Now you can say these waves are said to be in phase. In phase. So what happens? Constructive interference. So for that lambda, for that theta, only first row, fifth row, 10th row, 15th row, 20th row producing the deflected waves which are traveling backside are in phase. When they are in phase, it causes constructive interference. They all strengthen and then go and hit the screen. At the same time, for that condition, for that lambda and for that theta, secondary wave produced by row 1 and row 2, you know what how they are? Like this. They are completely out of phase. So they cause destructive interference. So they cannot go and reach they don't have the strength to go back and hit the screen. That's why when you place the crystal at that lambda, at that theta, only those rows or those planes which are separated by a particular interplanar distance producing secondary waves which are in phase, so they go and hit the screen but take one spot. That one spot contains information about that set of planes. Right? For example, in this screen, this is maybe 1 to 1. This is 1 to 1. This may be 386. This may be 11, 14, 18. These are Miller indices. Miller indices, correct? So different sets of planes causing one dot. That one dot contains the electron density information about that particular set of planes. Not one plane, set of planes. At this moment, I'm sure you may be knowing, but still, it is my duty, very simplified way. I have to tell you the Miller indices. I'll just few minutes. Oh, 4 I think we started for 320 or 315. I'll finish in 10 minutes, then you can ask me some questions for another half an hour or whatever. Fine, wait. Am I audible?
Yes, sir.
Am I visible?
Yes, sir.
Yes, sir.
Am I visible now?
Now only it is visible, sir. Yes, sir.
Okay. All right. So, hope you can see this torsion.
Sir, konja left side nathikalam, sir.
Okay.
Unga left.
So move. Okay, sir. Okay, sir.
Okay.
Yeah.
Can you see a box here, sir, please?
Yes, sir.
Yeah, please. Okay. Dear friends and colleagues, take this is a unit cell. Unit cell. Fine. This is A. This is B. What is going behind is C. A, B, C, unit cell. I'm sure you know this. It's very simple. Okay. Let me take this unit cell. Okay. I think you can see now. Another unit cell. All right. So unit cells are going like this. And then unit cells are going this way also. And then behind also. Okay, fine. Now, if I'm asking someone to cut A axis means this is A, this is B, right? So this is B axis.
So we are not able to hear your voice, sir. Hello? Sir? We are not able to hear your voice.
How about now?
Yes, sir. Yes, sir.
Okay.
Yes,
Okay.
sir. Please proceed.
So this is a-axis, right? So we are going to ask someone to cut the a-axis.
Yes.
All right. So I see. Now only you can see the screen only, I guess. That could be it.
Yes.
Okay. Now I think you can be seeing, I guess. All right. So this is a-axis, right? So I'm going to ask you to cut the a-axis only once. What will happen? Let me go and scan. So I'm going to cut here, right? So when there is a unit cell, I'm going to, I think it is not possible. Maybe too much light, I guess. That's the reason. Oh, fine, no problem. I'll take this one. So there is one unit cell here. So this is a-axis, let's say, is going continuously. So if I am going to ask you to cut the a-axis only once, so that one unit cell can be separated, where you will cut here. Because these the right. So this is the continuous. This is a-axis. I'm going to cut the a-axis. I'm not cutting B, only A. A means this. Correct.
X-axis.
So this is the A. So I'm going to cut. I'm going to cut.
Horizontal axis, sir.
Correct. I'm correct now. I'm going to cut here, so that one unit cell will be separated.
Yes.
So once I'm getting one unit cell, obviously you have to connect the other unit cell also. We have to cut another unit cell cut. That means you will cut at the end of every unit cell along the a-axis. Planes. All these planes together are called as 100. Correct. Suppose if I'm asking you to show me 200, that means if A is 20 angstrom length, I'm going to cut at the 10 angstrom middle and the end. Again, middle, end, middle, end, middle, end. Each unit cell, middle, end, middle, end, middle, end. All these planes together called as 200. 200 is not one plane, one set of parallel planes. Correct? Correct. Suppose the other way, 0, 1, 0 means I will cut at the end of the B axis, one unit cell. Correct? If there is the A and B, I'll cut here, I'll cut here, I'll cut here, I'll cut here. Only B axis. I will not touch the A, I will not touch the C. Okay, okay, fine, no problem. Now you can imagine, now Bragg's law tells you for each lambda and theta, one set of parallel planes which satisfy with the particular d, interplanar distance, which satisfy the Bragg's law will give you diffraction. That spot contains the information about the electron density in that set of planes. That is diffraction happening. To understand for our further uses and calculation, the new concept called Miller indices was introduced. See how beautifully different bits of piece of information brought together to form the crystallography. All right. Now, I think you just tell me when I'm supposed to stop, I'll do. Then probably we can use the entire other section for the discussions also. Okay.
So please, you shall take another 15 minutes, sir. No problem.
No problem. Great.
Thank you, sir. Thank you.
Okay. All right. Now, See, this is how it happens now, correct? So crystal is exposed to X-rays. Now we are getting spots. This spot. Now we have, this is the important portion which is called as indexing. Indexing, most probably, I don't know how, if you directly come to our lab, we can show you how to do and so on. But just in the flavoring, I'll tell you. So the first rows, right? These are all 1, let's say, it is 2, and then 3, and then 4. Miller indices. 1, 0, 0, and then 2, 0, 0, 3, 0, 0, goes on and on. First thing is crystal. Second thing is diffraction. Why diffraction happens? I told you. For a particular theta, and for a given lambda particular theta, we'll get one spot. What is that spot? That spot corresponding to one set of real planes inside the crystal. When I say real, just now I told you imaginary. Now you call it real. Means it is imaginary only, but that is the planes inside the crystal. So we call it as real. For each set of planes, there is a reciprocal lattice point. I'll tell you in a slight manner. You take a diffraction grating, and then you take a ordinary laser pointer. Which one you use for the laser point presentations, PowerPoint presentations? You just click here on the screen. Lines are horizontal, whereas in the screen you will see slow dots which are vertical. Right? If you have 10,000 lines, but in the screen you will have only one single line parallel. I mean perpendicular. Perpendicular. You know what? So a two-dimensional array of lines will represented by one tilted line. These horizontal lines will give you vertical line, one line, right? So this is called as reciprocal. This is real. In the grating you have real. In the screen you are getting reciprocal, right? I'm talking about lines, which gives many lines, will gives one line. In the crystal we are talking about planes. Many planes will give you one spot. That means one point. That is called as reciprocal lattice point. But see, sir, I don't understand reciprocal lattice. I don't understand the equations of correspondence. You don't need to worry about anything. You can even completely forget about the reciprocal lattice concept. But why it is important, why it is introduced, what you are recording on the film is reciprocal, not the real. From the reciprocal, you are going to find out the real. That's why this concept is introduced. It is not necessary you should understand it. Even if you don't want to understand, there is no harm in that. As long as, because X-ray crystallography is the best, is one of the signs for which many online tools, online softwares are available. All right. So without any understanding anything, you can do crystallography nowadays. Even a life science student, a biochemist, without doing anything, you can. As long as he has the crystal, if you send the crystal to synchrotron radiation, they will collect the data and send you back. You can solve the structure using n number of softwares without knowing crystallography. No harm in that. Anyway, fine. So that's why that Miller indices concept and the reciprocal lattice concept just I introduced. You don't need to understand even this, but you should have the appreciation. That's why. Correct. So, for example, sorry to say, it is not uncommon. Many people think 100 means one plane. 281 means one plane. It is not 281. It is not one plane. No, for example, now for our thing, let me take 110. 110. You know what it means? 110 means every unit cell should be cut at the end of A axis and at the B axis. That is called as 110. Yeah. All right. So 110. So now I can show you this, right? An unit cell. This is the A axis, and then going upward is the B axis. So this is the end of A for the unit cell. For the unit cell, this is the end. For the end of A, correct? For the end of B is this part. So this part and this part. This part, A end, this part, B end. Now if I cut like this, diagonally, if I cut this way, If I take a knife and then let goes like this, so which will cut A one time, B one time, C is never touched. So it's called 1, 1, 0. 1, 1, 0. Fine. Suppose 1, 2, 0. A should be cut one time, B should be cut twice. Let's say what happened. So A is ending here, B ending here. Now B middle is here. B middle is here. Correct? So what happens? First knife should go like this. It should cut from here to end of this. Okay, fine. Then what happens here? This cut should not go here. Should not go, because I told you parallel. That means first knife cuts from here to here. Second knife goes from here to another unit cell. Another unit cell. Now look at the total. Every unit cell cut at one time at the end of A and 2 times in the B. Correct? Even 180, you can say 180. That means 1 is here, 8 times you have to separate. 1, 2, 3, 4, 5, 6, 7, 8. Correct? So 1 will end with this. Second will go somewhere to the other unit cell. 3 other unit cell. 4 other unit cell. Not necessarily in the same unit cell, because we have unit cell underneath also. So 180, if you look into clearly, every unit cell may be next, above, below, behind. Every unit cell that will have a cut at the end of the unit cell A, and then B will be sliced 8 times. C will never cut. Never underwent cutting. That is what, right? So now if you just go for the youngsters, maybe for the research scholars or MSc students, it will be used. Oh, it's a faculty development program. So that means you all already know. I'm just refreshing your forgotten thing or maybe unfamiliarized. All right. So what happens now? Now Miller is at one side, X-ray diffraction is one side. Because of the in phase, we got the spot. Okay. Let me come to the climax. The climax is this. Hope you can see the screen. I think I'm not sharing, I guess. Entire screen. Okay. Fine. Now let me finish. Maybe so. Okay, sir. Now I told you, sir. So each spot is indexed. I told you, right? 100, 130, 180, 190. For example, A index is 20 angstrom, let's say. So now you can say in your data, the H ranges from -20 to +20. -20, 00, -19, 00, -18, 00. Suppose K is, unit cell is 5, let's say. -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. K ranges from -5 to +5. L, suppose L cell is, index is 6, -6 to +6. Now the combination, don't forget, this is, I told you, H is -20. -20 minus, 5 minus 6. And then -20 minus 5 minus 5. And then -20 minus 5 minus 4. This is a combination of all. So you will have many spots. Each spot is one index. So such a line, HKL. How many HKLs will be there? Many. Thousands and thousands of HKLs will be there. And then what is this? The intensity of the spot. Intensity of the spot. Okay, fine. Now let's see. So this is the total spot, right? Bright spot means heavy scatterers present. In that set of planes, suppose bromine, copper, nickel, is that such big scattering atoms are presenting that set of plane. That's why that spot is very bright. Can we say that? No. I told you already, the brightness, softness or lightness refers to what extent the waves are in phase. That set of planes may contain lighter atoms. If the secondary waves which are coming from these planes are pakka in phase, you will get a bright spot. Your planes may contain heavier atoms, heavy scattering atoms. Scattering means X-ray scattering. There may be heavy scatterers. But if the waves are coming from that set of planes are only to some extent in phase, you will get only lighter atoms, light spots on the screen. So I told you the spot contains the electron density information about that set of planes. That is one side. Another side, the brightness or lightness not only depends on the nature of the scatterers, but mainly depends on to what extent the waves coming from that set of planes are in phase. That is important. So if you want to so this is what it is. Oh my God, where is it? Yes, this one. This F is actually, I told you the intensity, right? I, in the HKL I, you have seen this. This one I. Just for, you roughly take square root of this, you will get structure factor, we call, that is F. This F depends on amplitude of F, but exponentially I phi. Phi means phases. So the brightness depends on the F means scattering atoms, scattering power of atoms, right? In that set of planes, many atoms may be there, right? Some atoms are fully, some atoms are partially, whatever. Each atom has scattering power. So add on, all these add on, you will get the scattering of that set of planes, correct? That many set of planes. Suppose 100 or 800 or 81 minus 11. That set of planes may contain, right? Because I told you, molecules are arranged like this. So when you are slicing different planes, some planes may have some atom fully, partially, concho, slightly, whatever. But the thing is, what is the scattering power of an atom depends on atomic number. Lighter atom, light scattering. Heavier atom, heavier scattering. That is true. Atomic scattering factor, that is true. What is structure factor? Structure factor is addition of scattering factors of all the atoms partially or fully present in that set of planes. Correct? This is the total scattering power. This total power not only depends on the scattering power of atoms, but mainly depends on to what extent the waves are in phase. To what extent the secondary waves from that set of planes are in phase. That is important. So F, the intensity, let's say, the intensity directly proportional to the scattering power of individual atoms, but it is exponentially depends on the phases. Now you know which is more important, not the scattering power. Which is more important, exponentially important? Phases. Important? Phases. Unless and until you know the phases, you cannot calculate the electron density. That means you cannot calculate determine the three-dimensional structure. Okay. This is the electron density equation. This electron density equation means electron density at any given point within the unit cell. Within the unit cell. Correct? This is equal to 1 by, forget about all these things. Summation of F of HKL. F of HKL. How many HKLs will be there? For that data, maybe 3,000, 4,000, 8,000, 9,000, 10,000. That many set of indices, correct? So everyone's contribution at any given point, you have to consider the contribution from all set of planes. That means from all Miller indices. So the summation of all, not only that, but each set of planes, I told you, for each spot, the brightness or lightness depends on the phases, so corresponding phases are important. Correct? Phases are important. So electron density can be calculated only when phases of individual reflections are known, which cannot be measured from X-ray diffraction method, for which we have to use only crystallography. Ipadan crystallography start. Right? Okay, fine. Now, just tell me, I'll just say one simple thing which is so important. I told you, for example, this is an important discovery which got the Nobel Prize. See, I don't know phases of this. I don't know phases of this. I don't know phases of this. Means, for example, there is a reflection. Reflection means indices. There is an index called 111. I don't know the phases of phase corresponding to that spot. 111, I don't know. Okay. You tell me another one. 222. I don't know what is the phase of 222. Correct. I'm going to ask you one thing. You know the middle, there is a middle spot, is there, right? It is a completely, we actually hide it because it will be too bright. If there is a spot in the middle, what it will be? It will be undeflected wave, which penetrate through the crystal without any disturbance. It goes and hits the screen. If there is something which is imaginary, if suppose something is happening, that will be the brightest spot. And then what it will be? What will be the phase of that? Phase of that will be 0. Why? Because in that case, the waves will be, the phase difference is kandipa 0. Absolutely. There is no any phase difference because it is not deflected. Correct? You got my point? So if there is a spot at the middle, that means 0, 0 index, the phase is 0. Correct? Okay. Now let's come to the point now. If you just tell me one index, you name it one index. Someone say 111. Another one say 2 minus 1, 4. Let me pick the third one, which is minus 3, 0, minus 6. This is one Miller index for which we don't know the phase. This is a Miller index for which we don't know the phase. This is another Miller index for which we don't know the phase. But if you suppose add, what will happen? 0, 0, 0. Correct? That means I know what is the phase of this. What is the phase of this index? 0. So phase of this index plus phase of this index plus phase of this index will be equal to 0. Now I don't know. Now I minimized. Now I don't know the individual phases, but I know that if you add these phases, it will be 0. Now the rudiment, huge thing, it has been brought to very simplest way. This is called direct method. I am telling you lighter way. This is called direct methods, for which Nobel Prize was given in 1985. Without direct methods, we cannot solve the structures now. You can solve. It will take years together. Now, just 0.5 seconds, we can finish the structure determination. All right. Now, once you get the structure, suppose only partial structure is available. So I don't know the remaining. I have some portion is missing. Some portion I'm not sure. Don't worry. Now, if you compute the electron density with instead of structure factor observed, you can see this difference. You know what it is? From the data, I got the structure now. From the structure, I can recalculate the data. The difference between these, this is from the machine. This is from the model, which I got it now. You got my point? Data, from the data, I got the structure. From the structure, I can recalculate the data. Now, the difference in this data is called R factor, which will tells you the correctness of your structure. I don't want to go in detail unless and until you ask some question. Fine. Now, if I compute the electron density for only the difference, if there is any missing portion, that will appear. If I connect them, I'll get the complete structure. Got it? This is called difference Fourier synthesis, so which we'll use to solve the crystal structure. All right. So I'm done. So I can take any question from you. If there are no more questions or something, let me take another 10 minutes to show you a demonstration. That's up to you. Do you want me to show the demo for 10 minutes or do you want me to take some questions? I'm done. I'm okay for whatever. Even another half an hour, I have no problem.
No.
You want questions or demo? You just
Sir, participants have some questions, sir.
Oh, please.
Yeah.
So the first question is how to calculate the crystal structure angle, for example, rhombohedral structure. How to calculate its angle from experimental data?
I think the question is from the powder diffraction. Am I right?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Honestly, I don't know. One, because we do only single crystal XRD. I don't know powder XRD. Number one. Number two. Okay. Normally, in the powder diffractometer, we have the 2 theta values okay, on the x-axis, and then we have p. And the best thing is, we can identify the compound only if the reference data is available. If the reference data is not available, you cannot say what the compound is. One. Fine. Second, because at this 2 theta value, there will be P for nickel chloride or nickel pentahydroxychloride or gadolinium pentoxide, whatever it is. So without reference, you cannot say. Fine. That is one thing. And then, even for example, in the case of the diagram which I showed you, the X-ray diffraction pattern, we have 2-dimensional data here. Is a plane. So you have a 0 in the middle, you have some spot, some spot, some spot, some spot. So you can connect them, to find out A, B. Let's say A, B. C cannot be determined because C is in the out of the 2-dimensional figure. But C can be predicted and then later on verified. Why? The moment if you rotate the crystal, what will happen? The C axis will come into this plane. Correct? So you can have that point now. Now you can find out A, B, means A, B is shown now. When it is rotated, crystal is rotated, but the X-ray film is stationary. So what happens? The other reciprocal lattice point corresponding to C direction will come and hit the screen. At that time, you can find the C. That's why we call indexing and then re-indexing. A, B can be seen and then C can be predicted. Later on, we verify C also. At that time, A and C, A, B also refined. So it's called re-indexing. Okay. In the case of powder XRD, you have only one, not even two, only one. Correct. And then, is it not possible to find out ABC from powder XRD? Of course you can. Of course you can. You know what? The powder XRD pattern is what? From many crystals. From orientations are different. From many crystals. But if you want to have that, right? In the case of single crystal, there is no point or no difficulty to find out any angle or whatsoever. Because I showed you, right? When indexing itself, we find out ABC alpha beta gamma directly. Because it is 2-dimensional, I mean, the 2-dimensional, then you are rotating in all possible way to record the 3-dimensional also. Right? In powder XRD, it's tedious, but still you can measure, of course, but I really don't know.
Sir, are you able to hear?
Can we calculate ionic radii from XRD data? The next question is.
See, from single crystal data, anything and everything can be measured. Anything and everything can. For example, I'm telling you. For example.
Sir, please unmute your mic, sir. Sir, please unmute your mic.
Okay, fine. Okay, fine. So now once we got the structure, because it's just coordinate, it's called fractional coordinates. from crystallography, because in crystallography, X, Y, Z, that is not X, Y, Z. Suppose X is 0.5, let's say, it is not 0.5, 0.5 times of A axis. Suppose Y is 0.1235, it is not 0.1235, it is 0.1235 times of Y. So it's fractional coordinates. Once you got the structure, you can calculate the distance between these 2 points. See, 1.45, 1.405. Or maybe you just distance between these two, 2.4 and 4. Suppose if you want to see 1, 2, and 3. Now it is 116 degrees. Correct. Suppose if I want to see, maybe this, let's say. The distance between these two atoms, it is 1.279. That means it's double bond. Is single bond, is double bond. So, see, what I am talking about is geometrical parameters. Your question is crystal parameter. Means ionic, inter-ion distances can be calculated like this. The first question what you ask is from the crystal, A, B, C, alpha, alpha, beta, gamma, that one. The second question is ionic radial distance. Once you have the single crystal, once you have the structure, anything can be seen. Angular distance whatsoever, because it's a mathematical is 2 points. That's all.
Sir, the next question is, which software is used to solve the structure?
Okay. So it is given here. It's called WinGX. WING. I hope you can see the screen here. It is free only. It is free software you can download from anywhere. Only from academic institution, in your college or maybe university. You have to use that IP. That IP address, institution name should be given only for reference. They are not going to charge you anything. It is free only, WinGX.
Software.
WIN capital G capital X. You can see here, the corner. Yeah, it is the WinGX. It's available for any operating system. It is free only.
Okay. So the next question is, why composite materials peaks are not shown in XRD pattern sometimes?
Okay. See, one thing, when something is not picked up in X-ray, that means it is not crystalline. One, it is not crystalline, so you cannot get any diffraction peaks, whether it is powder XRD or single XRD. Suppose, and then sometimes you may have crystalline state, but it will be highly twin. If it is twinning, you may have this problem. Otherwise, you have high mosaicity. If high mosaicity is there, the crystallinity is very, very minimum, and then your diffraction pattern cannot be. Obviously, when you say the composite, probably when these individual compounds may have crystalline nature, when you make it as a complex, like a composite or whatever, probably the crystallinity is completely gone, or mosaicity would have become very, very, very high, or twinning could be a problem. Crystal twinning could be a problem. Because crystal means pure. Composite seems like it is not impure, right? But still, once you mix it, make it a compost. For example, if you crystallize Gunasekaran will be there. If you crystallize Gunasekaran Subhashini, my wife, so husband, together will be there. So it's together, it's not impurity. It is together one. So even as a composite, if it is crystalline in nature, it will be picked up by X.
Thank you, sir. So, no more questions from chat box.
Okay.
Thank you very much, sir.
So you want me to show this for another 5 minutes or not?
Yes.
Yes, sir.
Okay, so just going to take 5 minutes. So for example, I showed you this already. Okay. So this is the HKL file in the normal Yeah. So this Word document, so you can see this is HKL index, right? See how many lines? See? So one crystal has been sliced into these many planes. HKL intensity, fine. And then the corresponding instruction file may contain these details. Very simple. Probably if you send a crystal to someone, they will give you back only these two. So this is called instruction file. You can see this. Here you have lambda, A, B, C, alpha, beta, gamma. Correct. So once you have this is the information, and then you have the information about the space group, lattice type and phase group, whatever. Okay, don't worry about all these things. I told you direct method. Individual phases can be calculated by the combination of triplets to get 0, 0, 0. I told you, right? This is the simplest light way. Fine. Once you have the instruction file and HKL file, you just load it and then go and then solve the structure like this.
Okay. Sir, one more question in the chat, sir.
Yeah, please.
Yes. I have one question. Except change in intensity or shifting, is there any other parameters which are helpful to determine that doping is successful?
Okay. Say for example, I don't know the exact direct answer, but I'll tell you one thing. In the case of protein crystals, we use one technique called crystal soaking. Means take a protein crystal and soak in mercury solution, mercury chloride, let's say. Now, mercury atoms are penetrating into the crystal via the solvent channel and then sits here and there. Correct? Good. Now we are collecting the data. What is the data? You mount the crystal, you take a shot, rotate, shot, rotate, shot, rotate, shot, right? Certain planes, at certain lambda theta, some planes which passes through the mercury atom will be picked up. At that time, if you compare the non-soaked data and soaked data, you can see the big difference in the case of intensity. Because now that comes from the mercury, right? That will tell you doping is happened. Doping is happened. Okay, fine. Now, to what extent it happened? From single crystal XRD as such, we cannot say. We cannot, whether it has happened or not can be seen, but to what extent or degree of doping? Is it possible to calculate the degree of doping using diffractometer? As such, we cannot. But if you refer the Kittel book, the very old book for the solid state physics, and we have beautiful portion on crystallography, where there is a beautiful portion called systematic absences or systematic presence. There you will tell you, no, that will tell you about the space group. That is the main purpose. But inside, you will have the calculation of structure factors, right? Now, using the crystal volume, crystal density, and the total diffraction, now the degree of doping can be speculated to some extent, which I really don't know. For the protein crystallography, we want doping, we want to see whether dope, even we don't call it as doping, we call it as soaking. Doping is different. All right. So when we have this window, now what we're doing, we are doing solving. Now you can see there's a direct, there is direct methods. When you say solve the direct methods, now the structure is solved. Structure is solved. In what sense? 3.4 seconds because of direct methods. And then what is the direct methods? I told you the simple approximation. Now you can see the number of atoms. Oh my God. Oh, thank you. Now the number of atoms you can see it is 26. 26. And now you can see there's another factor called 0.212. If you multiply this 100 by percentage, it is 21%. This tells you my structure is 21% wrong. To see this, you can see, click here, you can see this is the structure, right? As I have seen here, only 26 atoms, whatever bigger than 26, you can simply delete. That means 28. And I'm just taking one extra minute, please. 30 and 32, 34, 33, and even 35. Okay, let me delete these atoms, selected atoms. Okay, now let me select 29 and 27 and 31. Let me delete. All right. See now, this is a complete structure. Now the structure is solved. But anyway, there is another half an hour to go for refinement. I don't want to go in detail. Now you get the three-dimensional structure within 3.4 minutes. Why? Because of direct method. That is the thing I want to tell you. Yeah, even a simple approximation can solve a so big problem just like that. So that's why they got the Nobel Prize. Anyway, so basically I'm done. I don't want to go in detail about the refinement and so on. Simply, and if you have any other question, I am happy to help you. One second thing is, I am at Crystallography and Biophysics, room number 3 and room number 12. If you visit physically, please don't hesitate to visit me in our lab. We will be happy to solve your problem or to train you as a crystallographer, maybe within 5 to 6 hours. Only the software, not the complete theoretical lab. And just go to Google and type your scattering and diffraction. You will get one website called IQCR. For example, oh my God, very slow. Yeah, so this is the one. xtel.iqfr.csic.es. This will give you the answers of all your protein crystallography, powder crystallography, or single crystal XRD. This is contain 10 chapters. All are animated, interactive. See, this is the 5th chapter. Totally 10 chapters. You will be wonderful crystallographer if you go through all these things. It will give you a lot of questions, equations, how to solve in a simplest manner. Don't get panic. Call animations and then see these are scattering pattern with every single details about thermal parameters or whatever the question you ask me, you will get the answer with this website. This contains 10 modules. It will take 6 months for you if you go through enjoying every day 2 hours. You will be wonderful crystallographers. All the best and thank you. This is xtel.iqfr.csic.es. All go to Google and type scattering and diffraction. You will get this site. Thank you so much. All the best.
Thank you very much, sir.
Thank you, sir. So, good evening to our most valuable resource person, respected head of the department, and teacher participants gathered over here. It's my privilege to propose a vote of thanks on the first day of faculty development program. Today, we had a fruitful and informative session, sir. Our resource person, Dr. K. Gunasegaran, Madras University, shared interesting animations and informative demonstrations. He also explained the essential of structural information, extra crystallography procedures, Miller indices, etc. Especially the interest you shown while demonstrating crystal structure, unit cell and all, really we inspired, sir. At the outset, I thank our resource person, Dr. K. Gunasegaran, sir, from Madras University. We are really enlightened with your knowledge and presentation, sir. Thank you so much for accepting our invitation and your gracious virtual presence. I extend heartfelt thanks to participants who were joined from various institutions from various states. Thank you very much for your active participation. Give your cooperation and support for forthcoming days also. Once again, I thank everyone joined here.
Thank you very much, sir.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you,
sir. Thank you, sir.
Yeah. Shall we wind up, sir?
Why not? Thank you so much.
Thank you so much.
Thank you, sir.
Even though we are in online, Actually, we are lively attending your session, sir. It is excellent. Thank you very much. Thank you.
Thank you, sir.